My name is Dhanushka Samarakoon, and I currently work as the head of library technology for the University of Miami Libraries. Today, I'm going to talk about machine learning based descriptive metadata generation for library archives. I know that's a long title. So why don't we break the topic into sections? So what's our goal here? We are trying to generate metadata for library archives. Normally, this is a manual process, but here, according to our topic, we are looking at how to utilize the machine learning process to generate descriptive metadata. So why do we need metadata? What's the need for it? In most cases, it's used for searching and easily locating the information that you want. When it comes to metadata, there's two main types. We have the technical metadata, which can be automatically derived or generated during the digitization process. But here we are going to focus on the descriptive metadata, which describes the photograph. The users wants to know what the photograph is about. They want to know what it represents. So when you have thousands and thousands of photographs, it is helpful to have this descriptive metadata. So the users could easily search and locate the photograph that they need. With that being said, let's see how a typical digital library workflow works. I know this might not be the exact scenario, but this is just a very high-level overview of how normally things work. The first step is the acquisition. Maybe you purchase the historical collection from a vendor or it's donated, but some sort of acquisition process. And then it goes into various administrative and legal work. This could be expanded further, but since that's not going to be the focus of the presentation, I won't be getting into detail about the administrative processing. But essentially, you go through the steps and figure out things like copyrights, rights of use, and terms of conditions, things such as that. Next, you digitize the photograph, which essentially means scanning the photograph according to the specifications that you have defined in your digitization process. So as soon as you scan the photograph, you can make it available to the public, but that wouldn't be much of use for anyone, especially if you have a large collection. If you have only a very limited small collection, let's say you only have 100 photos, then users could just scroll through the images and locate the photos that they want. But if you have a large collection of like thousands and thousands of photographs, no one will be able to locate what they are looking for. So that's why we need to move to the next step to add the descriptive metadata. So archivists or curators, they look at the photographs and they describe what's in there. If there are any individuals, they try to identify them and try to describe what's happening in the photograph, what objects are available. They add all of these descriptive metadata to the photograph, and then you make it available to the public. So what's the problem here? The problem is that in the digitization process, the scanning could happen with unskilled labor. For example, once you set the correct parameters, you could have a student employee complete the digitization process. But when it comes to adding the descriptive metadata, you need skilled individuals who are skilled in that domain, or individuals who have the local knowledge and know the best practices of metadata generation. But when you're working in large volumes, that's where the bottleneck is. It will take more time to describe the photograph than to digitize it. So once you create that bottleneck, it will increase the amount of time that it takes for you to add the photograph to the public repository. So that's the problem here. So what's the solution? Here, the solution is once the photograph is digitized, we try to train a machine that could generate some sort of descriptive metadata. So the image could be released to the public repository and patrons could start using it immediately. Now keep in mind, this is machine generated metadata. It won't be as good as human created metadata. But the goal here is to reduce the delay between digitizing the photograph and make it available in the public repository. That doesn't necessarily mean that that will be the end product. The photograph is available in the public repository, but someone could later come back and review that information. They could improve the descriptive metadata that the machine generated, or add new metadata to the photograph. Now, since we talk about the problem and the proposed solution, let's take a step back and head in another direction. Let's talk about what machine learning is. Here I have a simple diagram that describes what machine learning is. So again, machine learning is a broad field, but here we are focusing specifically on image recognition. So you're giving an image to the machine. This is shown by the blue dots on the left-hand side. So input every single pixel of the image. It encodes that information and inputs into the machine. Then it goes through a series of decisions. At each layer, it's making a decision and moving on to the next layer. So are there patches of lines? Are there ovals? Are there triangles? Based on yes or no, it moves on to the next step. So as you can see, in each step, it's trying to narrow down the answer to the ultimate question. Is it a dog? Yes or no? So this is a simple machine learning model to identify whether a given image contains a dog or no. Okay, so here's another diagram or a workflow diagram. So here I have two objects. One is called ImageNet, and the other one is called the Inception Image Recognition Model. So I'll get into more details about these terms in later slides, but I want to show this as a starting point. So in the previous slide, we talked about the multiple layers and how the machine goes through the decision-making process. So Inception is one of the image recognition models. Here we are using the Inception Image Recognition Model. So how was that model trained? When you're talking about a model, that model needs to be trained. So essentially, going by the previous example, we are trying to train a machine to recognize dogs. We give it an image of an animal, and then the machine says if it's a dog or not. But for the machine to gain that insight or the knowledge, it has to go through the learning process. So during this training process, we submit lots of images with various animals. And we tell the machine whether that particular image is a dog or not. So this is the training data. Here the machine was trained on the ImageNet dataset during the Inception Image Recognition Model. So let's see what ImageNet is. ImageNet is a large dataset that has 100,000 images of different scenarios, different sceneries, and different objects. And we can use it to train the Inception model. All the images are tagged with words from the WordNet. So now let's take a look at what WordNet is. So WordNet is a structured vocabulary that was developed by the Princeton University. It has a hierarchical structure, and it's easy to frame the dataset or easy to tag the images using that vocabulary. So now that we talked about it, let's go back to the previous slide. So we have the Inception Image Recognition Model trained with the ImageNet dataset. So ImageNet is a huge dataset. I mean, it has a lot of images and the images tagged with nouns. So each object is defined by a word from the WordNet dataset. And the WordNet nodes are set up in a hierarchical manner. Okay, now here what do? We use the Inception model and feed it with the library's own digital collections. So here we have to submit, we can submit an image from the library digital collection and ask the model to describe images based on the knowledge that's available in the Inception model, essentially to generate labels and captions. So for a given photograph, what would be the labels? It could say a building, car, person. It would generate labels such as that. and the caption is the complete sentence. For example, a car being driven by a person in front of a building. That's the difference between the two. So in the previous example, we were not doing any training. We are using the existing model and giving it a photograph from the library and asking the machine to describe it. But most of these models are trained on born digital images from your everyday objects and scenarios. So the present day, the current environment. But when it comes to library archives, most of these photographs are historical photographs. So if you are talking about a car would look much different in a historical photograph versus the photographs of cars that you would have fed into the model from your Instagram page. So because of this, we should try to train the machine or improve it further using our own digital collections. So if I explain it further, the library already has a large number of photographs with human-generated metadata or photographs described by humans. So we would use this as the ground truth. So what is ground truth? Ground truth is we are assuming that photographs that were described by humans, it is accurate, and that we are feeding them into the machine as training data set or as training images so the machine could learn. Once you go through that process, as you can see, the digital library collections together with the inception model, you train the model and then you get a locally trained model. So the difference between this and the previous model is how we train the model using local data. Now the machine has some understanding how historical photographs would look like. And then we can use the locally trained model to generate labels. So the goal here is that we should be able to get much more accurate results compared to the basic out-of-the-box inception model, which has been trained using your day-to-day modern objects, the photographs of modern objects. So now let's talk about model development. How does model development work? Model development is the process of training a neural network. In this example, you will submit images of cats with them labeled as cats and images of other animals as not a cat. Then the machine uses these images to develop the neural network to identify the cats. Once the training is done, you can submit a new image to the model, and it will tell you if it's a cat or not. Here you submit the image to the input layer at the bottom, and then you have the set of neurons. It passes through these multiple layers in the deep neural network, and in the output layer, it outputs the answer, like yes or no. So what do you have to do if you want the machine to identify dogs? Then what you do is if you feed it with the training data set of dogs, and again a set of images of animals saying whether it's a dog or not. Or else you can enhance it further. You can submit images of cats and say that this is a cat, submit an image of a dog and say this is a dog, and maybe an image of an elephant and say this is an elephant. So if your training data set contains those three animals, then when you feed an image to that belongs to one of these three categories, instead of giving a yes or no answer, it would let you know if it's a dog, a cat, or an elephant. So here, essentially, you feed new training data, and it will learn to identify dogs, elephants, or cats. It will build a knowledge base. So the important thing is you don't have to do any code modification. That's the main difference between the machine learning process and the traditional programming. So here we go a step further. If you remember this diagram, it's the same one from before. We have the inception model. We train it with the the digital collections, and then we get the locally trained model. In the previous example, it just generated labels. So here we are using a package called IM2 text. which is short for image to text, to generate the captions. So how does this work? Here I have a link. If anyone's interested in learning more about the package, you can just follow the link, or you can just Google IM2 text. If you are interested in exploring deep, feel free to research further into this. This is a show and tell model. So what does that mean? So what's in this picture? In this picture, we can see that there's a cat and there's a puppy or a dog and a wooden floor. So what caption would the IM2 text generate for this image? It will identify the objects first, the cat, the dog, and the wooden floor. Then it will generate a complete sentence, a dog and a cat lying on the floor. So that will be the output. So what is show and tell? Show and tell is a neural image caption generator. It applies an encoder and a decoder model. So here I want to explain the inference process in detail. So when I say inference process, that is the process of generating the outputs of like labels or captions. So I want to explain the inference process by introducing this model the code package is using. It's called the show and tell model, which has two parts. It has the encoder part and the decoder part. I'll explain it with some examples in the next few slides. So when an image is given, it first faces an image recognition problem. It has to recognize the image first. So here we have the image recognition model, which is the encoder to detect the objects in the image. Here it encodes it, and then you try to detect the object in the first step. It outputs cat, dog, and floor. So the object recognition part is now complete. Now we have to construct the sentence, which is the natural language processing, where you decode it, or you can use the model layer as the decoder to construct the entire phrase. So with that being said, let's take a look at some of the softwares that we used. I won't get deep into these softwares, but let's look at the prerequisites and the process that we had to follow. So here I have 4 main software that we used in order to get the project working. The first one is TensorFlow. TensorFlow is a free and open source software for machine learning. It can be used across a large range of tasks, but it has a particular focus on training and inference of deep neural networks. So when I say training, it is the machine learning process or the training process. The inference process is about deriving the output. And then Bezel. Bezel is a free software tool that allows for automation of building and testing software. So it does the housekeeping work on the backend. And we have NumPy, which is a library for Python programming language. It adds the support of large multi-dimensional arrays and matrices, along with large collection of high-level mathematical functions to operate these arrays. The machine learning processing in the backend conducts mathematical calculations, and NumPy assists these large calculations because that's the core of the package. And finally, NLTK, or the Natural Language Processing Toolkit. It's again a Python package that you can use for natural language processing. Here you can analyze a lot of unstructured data. It can transform them into more human readable text. And here are the specs that we used when we were working on the training process. It doesn't have to exactly be these specs, but this is just what we used. For hardware, we need to make sure that we have the storage and the GPU. So GPU is the graphical processing unit that we are using for training. We are using NVIDIA 28 Ti GPU. And we have a 2-core processor with 32 gig memory on the server. Then we are processing images, which means like we need lots of storage. So we have attached a shared storage device to store all these images. And in terms of software, we used Python, and it ran on the Linux platform. So here we will look at getting the training data, MS Coco. So MS Coco is another training data set that is free. These are just 2 images from that data set. It has about 330,000 images. And as you can see, the first one, you have that image, and then you have the associated descriptive metadata with it. The man at the bat ready to swing at the pitch while the umpire looks on. So you have that description attached to the image. And the second one is a totally different image, but you still have the associated metadata. A large bus sitting next to a very tall building. So we can use these during the training process. So now let's see how we prepare the data for training, specifically the MS Coco data. Here we have the first image, the image that we looked at in one of the earlier slides. So on the left-hand side, I have the image, and on the right-hand side, you see how to encode the data so the machine could process it. It has the ID, then the image ID, the file name, and finally the caption that you have given that image. So now I want to introduce something called TF record or TensorFlow records. The TF record format is required for the training process. It can be created by running this given script. So here's what happened. The image along with the metadata has to be converted into the TF format. So if you want to evaluate the model with your custom data, then you have to convert your own data into this TF format. Here I have the image and the annotation file, which carries the description. What the script is doing is script is combining the image and the annotation file together into its own data format that's used during this data build process. Then it outputs 2 things. One is the TF record file for each image and its associated metadata. Then the process creates, then it creates a dictionary file. So it's building the dictionary. Whenever it creates a new TF record, it's adding to the description, adding to the dictionary. So this is a file that contains all the descriptors that have been used throughout the encoding process. So here's an example of a TF record and a dictionary file. Here we have a sequence example. So that's the output of the TF record. And on the other side, we have the dictionary file that has the specific terms that you use during the description, during the process of encoding. Like all the terms that you used in the descriptions, they get added to the dictionary. So I am going through this content at a very abstract level, but it's a good starting point. You can read further into these topics and figure out what's happening under the hood. So now let's talk about the training configuration. So Inception checkpoint. Here Inception v3 or Inception version 3 is an image recognition model trained on ImageNet dataset from 2012. Here I have the link to the ImageNet dataset. It has 1,000 classes, so essentially the images are categorized into these different topics. You submit this image to the Inception v3 model and it will output something like an Eskimo dog or husky. These are like real outputs that you get for this particular image. So here are some training configurations. Essentially some Inception models that are available. For this instance, we use the Inception v3, which is the image classifier with 1,000 classes as the possible output. So the output would belong to one of those classes. There are other models available with higher accuracy, which has larger class size, which means it has to go through a larger network and it will be slow in both training and the inference process. At the same time, the smaller models, which have a smaller data set, would be faster but less accurate. So these are the pros and cons. It's up to you to decide which one do you want. So you have to do that balancing act. In our case, we use the Inception V3 model that has top 1 accuracy of 78% and top 5 accuracy of 93%. So what does this mean? That means when you give an image to the model, it will output 5 phrases saying that what the machine thinks that image is. So there is a 93.9% chance that the machine would get it right. At least one say phrase would be right in that top 5. Top 1 accuracy is when the machine outputs those 5 phrases, it ranks them accordingly. So top 1 accuracy is the probability of the first one being accurate, which is 78%. There are other models. We got this data from a published source. We did not run all of these tests to figure out the accuracy ourselves. And we only used the Inception V3 model. But Inception V4, it seems like it's more accurate. Again, some other models have even higher accuracy. And when you look at the last model, the accuracy is low, but I would imagine that's probably much faster. So if you want additional information, here are some links. You can follow the links and get the additional information. So here I talk about optimization for local context. As I mentioned earlier, the base Inception model is trained with your everyday born digital images. Essentially images that you would find on like Flickr, Instagram, Facebook, which are very different from the archival images. So we have to optimize the machine for our local context. So let's see how we achieve this. Data segmentation. So let's talk about data segmentation. We have large data sets available with us that we can use in the training process. So for ease of use, let's say we have 100,000 images that we could use in the training process. We can use part of it for training, but then we have to make sure that the model is good enough. So what we do is we use part of the data for training, then we set aside some images for testing. So these images already have the human-generated metadata. So what we do is once the machine is trained using one set of data, we feed the images that we kept aside for the testing process, and then machine would output its own captions. We compare it against the human-generated metadata to see how well the machine performed. So in order to figure out what works best, we look at 3 different methods of segmenting data. First one is based on collections. So we have multiple collections. Let's say we have 10 collections. Collections 1 through 8 we use for the training process, and then collections 9 and 10 for the testing process. On the second method, dataset 2, what we did was rather than reserving sets of collections for training and some other collections for testing, each collection we divided into 2. 80% of the photographs from each collection would go to the training process and the remaining 20% for the testing process. So the third one is similar to that, but instead of collections, we used keywords. We found 10 common keywords and got the result set, and then divided the result set in a similar manner, 80% for training and 20% for testing. So here, blue denotes data that's set aside for training process, and green is for testing. So now keep that in mind when we go to the next slide. So this is a graphical representation of how we segmented the data. So in this one, the data set 1, everything in blue, the collections 1, 2, 3, 4, we use that for the training process. The collection 5, we leave that for the testing. And here's the second example. Each collection, 80% of the images. So if the collection has 5 images, 4 goes for the training process, and 1 is set aside for the testing process. And here data set 3, same as the before one, same as the one that we showed before, but instead of collections, we get search results and split them into 80-20 for training and testing. So once this is done, now we have we have the inception model. So we train it with the digital collections. So then, and once it's done, we have the locally optimized model. Then from that, we submit a photo and we either generate labels or we use the IM2 text package and then we generate captions. So now, yeah, since we talked about the process, now let's take a look at some of the challenges that we faced. So here I have 3 sample photographs from the collection. So these have been used in the training process. So what's the caption here is that's the descriptive metadata that is associated with each of those images. Since all of these images are from a local context, a local collection, we know the individuals who appear in the photographs. So that's how they describe the images. We have Mary Jane McLeod Meeks, Mary Jane Powell, Mary Jane Sampson. So they are described by their names. Now you submit these images to the training process. So these 3 are just a representative sample, but you will submit thousands and thousands of images to the machine. And the machine looks at them and the machine goes through the learning process in order to identify images. So once that's completed, let's say you digitize a new photograph, and for example, this one, and you give this photo to the machine and you ask it to go through the inference process and generate a caption. And what you need to understand here is machine doesn't know what the photo is about. So based on the previous images, machine is looking at past patterns. It is looking at the mathematical representation of these images, and it's trying to predict it. So based on the previous photographs, it looks at the image. Okay, a circular shape on the top, which could be the head. Then you have the torso, the arms, the legs. It detects these shapes. And machine decides, okay, I've seen this before. And it would say, aha, I know what it is. It goes and says it's Mary Jane standing by a cow. So what happens here? In the previous images, rather than saying this is a person, this is a person, this is a person, we gave the machine proper nouns or the individual names. And the machine got confused, like whenever it sees this outline of a human, that's called Mary Jane. So it uses that same logic to describe the new photograph. So what we want to do is clean the proper nouns from the existing metadata. So now let's talk about the proper nouns. In the previous example, we saw the issue with that. So what we are trying to do is we are trying to remove proper nouns such as location, date, time, money from the descriptive metadata that we use in the training process. Then we are replacing them with generic common phrases. For example, replace a person's name with a common phrase such as a person, 2 people, or a group of people. Or remove attributed words like the youth couple, it would become couple, or a group of individuals. For example, if the description says Mike and Jane, we will convert it to 2 people. So for all of these to happen, they are using a natural language processing mechanism. And Spacie is the particular framework that we used in this process. And here are some examples. So in this one, we have the first column is just the ID, but we have in the before column, we have the metadata that's already associated with the image. And after processing, we have the second set of metadata or the caption. So woman holds baby in cradle board at youth bear dance. So in that one, we reduced it to woman holds baby in cradle board. So I'm not going to go through each and every sentence, but as you can see, we converted the captions to a more machine learning friendly format. For example, the last one, Mike, Jim, and Jane are photographed. So that got converted to a group of people are photographed. So now with that being said, let's look at some of the images and the captions that the machine generated. So in this example, we give the machine the following image and ask the machine to describe it. The first output the machine is generating is a group of people standing next to each other. And the p-value is the confidence that the machine is saying that it's true. And then we have a group of people standing in a room, group of people standing next to each other holding umbrellas. So as you can see, this is not actually correct. So what's happening here is that the machine, for the machine, it's all abstract information. It's all mathematical notations. So the multiple dresses that you see hanging on the wall, I think machine identifies them as individual dresses. And then with that, the mathematical notation through the notations and the equations, it's pointing towards a group of people. So whenever the machine sees that pattern, it tries to interpret as a group of individuals. So ultimately, in this particular example, the image recognition is a failure. The machine was not able to generate accurate results. So now let's take a look at the second example, the Campbell's fairy. So that's the descriptive metadata that is currently associated with the photograph in the digital collection. So this is not a fairy, it's a bridge. So why was this label added? So when we looked further into it, essentially that there was a ferry in this particular location. So the location is called Campbell's Ferry. So what they did was they described the photograph with the location name. And on the site, you see the machine generated descriptions, such as suspension bridge. As you can see, not everything's a good match, but the first one is accurate. So how does this help us? Now, let's say someone is looking for that particular location, then they go to the repository, they search for Campbell's Ferry, and then this image would come up. But if someone's just looking for historical photographs of suspension bridges or just bridges, this image wouldn't even come up. They would have to just scroll through thousands and thousands of images to find something like that. So this is an example where the machine generated metadata enhanced or it complemented the existing metadata to improve the search process. So if you go to the next one, it says Havana, Cuba. Again, human has tagged this photo with the location, not necessarily what's been represented in the photograph. So the machine generated a group of people standing next to a sheep, a group of people standing around a wooden fence. As you can see, the first line is not accurate. There's no sheep in this picture. But I don't know, maybe it's that white space in the background or the shape or the texture of the shirt that the person in the back is wearing. Somehow, machine is trying to interpret it as a sheep. That's not accurate. But in the second one, at least it's gotten better. Although it's not a wooden fence, it's a metal one, but a group of people standing around the fence. So I think if you are using keyword-based searching, this metadata is good enough to locate this photograph through those keywords. If you search for people or fence, this would come up. And here's another image. Again, Malecon, Cuba. That's the existing description of the photograph. The machine said a couple of people are on a surfboard. A couple of people that are sitting on a surfboard. So the couple of people, that part the machine got right. It identified it correctly. But then it's adding the surfboard into the description. And there's no surfboard here. So what's happening here? Again, machine is probably interpreting the horizontal, the flat surface set against that backdrop of the ocean as a surfboard. And here's one where the machine was totally inaccurate. The current existing metadata described it as Kabuki theater. But I don't know what's going on here. Maybe it's the perspective that the photograph was taken, or the fact that they are dressed the same and sitting next to each other. But the machine generated description is completely wrong. It's saying it's a room filled with lots of different types of luggage. So again, now with all of these, what's our approach to fixing some of these issues? So what we decided is that machine will not generate 100% accurate data all the time. Sometimes it generates good enough data. So how can we improve the digital library workflow process and make it more efficient and faster by accompanying this data? So what we did was we designed a curation or a moderation platform. Someone could go to this platform, then it would display one image at a time. Here I have the image at the bottom, but on the system it would go on the top. And underneath that, it would display all this information. So when you click on the drop down, it would show all the different captions that the machine generated. So this is much quicker now. Individuals have a starting point. So if you want to use student employee to process these images, they would sit in front of a computer, they would open the software, and it would show them one image at a time with the machine generated information. So they can click accept or reject for those labels. And when it comes to the captions, from the 3 captions, they can pick the best one, and they can even edit that further. And so once it goes through that process, it can update the information in the digital repository. And if you want, you can store them and use them again in the training process, hoping that it would increase the accuracy of the machine. No, so I talked about the steps that we took. So I just want to show you this project. So we received a grant in order to do this project. It's called Project Chico. We received a grant through Lyrasis. We went through this process, and we have some outputs. Let me click on the link and get to the web page. Okay. Here we have published all our findings. So Chico is the web page. We have an overall description, but what I want to show is when you go to the download section, there's 2 links. First one is the Vagrant box. So what is the Vagrant box? So in this presentation, I talked about multiple softwares and packages that we have had to use in order to set this up. So Vagrant box is a neatly packaged environment with everything in it. So think of it as like if you get a computer, you have to install Windows, then you have to install Photoshop, Word, PowerPoint, all these individual software. But if someone were to install all of that and then create a snapshot of the whole computer, you can just deploy that software snapshot, and then you have the operating system and all the software. It's much easier. So that's what we did here. You can restore this Vagrant box, and within that we have we have included all the softwares. We have set the correct paths. Then you just have to point it to a model and start using it. So now going back. Okay, on the download section here, we have the pre-trained models. So we have 7 models. These are some of the models that we created. Anyone could download them and use them for the inference process with their own images. So you don't have to go through the training process. You certainly can, but we went through the training process in different scenarios, different contexts, and we have these 7 models available. So I'll just give a high-level overview of what it is. So PTM is essentially pre-trained model. So here the starting point is Inception v3. and we trained it with the library digital collection. And for the training process, we use caption that were cleaned through the NLP process. So we remove the proper nouns. And then we trained it for 1 million steps. And here, it's pretty much the same thing, but we trained it for 3 million steps. So what does this mean? When you are going through the machine learning process, you can determine the number of steps. So what it is saying is, let's say you give it a photograph. I'll go back to that dog example that I talked earlier. Let's say you give a photo of a Doberman and you tell the machine that this is a dog. You trained it with 1 million steps. So you ask the machine to look at it at 1 million times. Machine looks at it and say, okay, now I know what a dog is. You force the machine to look at it even further, more granular. So at a certain point, machine is not going to be able to recognize any dog because it's getting hyper focused on how a Doberman looks like. So it's an act of balancing how many steps you want. There's no right or wrong answer depending on the project and what you are trying to do. You have to figure out that number. So this is just two examples with 1 million steps and 3 million steps. Here again, inception v3 and trained with library digital collection, but here we use the unclean data. So captions, the original captions with proper nouns. Again, 1 million steps. So in this one, we trained it for 1 million steps and the same starting point, but we did not train it with the library digital collections. Instead, we used the MS COCO data for training. So the next model is similar to that. The only difference is the number of steps. We trained it for 3 million steps. And in this one, the starting point is the model that's trained with MS COCO data for 1 million steps. So we use this particular model as the starting point and then further trained it with library digital collections with cleaned metadata for 2 million steps. And here again, with clean metadata for 1 million steps. Let me drop these links to the chat. So that's the link to the website. And then we have published the findings over here. If you want to read more about it, here's a direct link to the PDF too. And that's it for my presentation. Thank you very much. I'm happy to answer any questions you have. If there are no, okay, I see one question. How long does it take for the computer to assign metadata versus human? So how long would a human take to describe a photograph? I think that would widely differ based on their experience, how familiar they are with the collection. I don't know, I would say anything between 5-10 minutes to, if they want to 5-10 minutes for a basic description versus very detailed description. But when we are talking about computer generated description, it would output, it would process one image in like under 15 seconds or so. And especially if you want to put more resources into that process, if you have very high powered computers, you can bring that time down further. So in terms of testing the accuracy, there are a few ways you can do it. One is, so I assume like this is testing the accuracy of the model where we already have human generated metadata. If one is to get a random sample and compare it manually. And the second one method is use a natural language processing tool to identify the key highlights from the both captions and compare them against each other programmatically and output a score. So there are, I would say those are the two main methods that could use. Right. Thank you, everyone.